started panicking when I was kind of coming here with the metro, realizing that I have a talk and there is nothing related to the Red Fest and Karl-Heinz's work. And I realized that maybe I should have actually talked about something else which we are doing and is related to Karl-Heinz's work, but I think there is a collaborator of ours who is going to talk about it in any case on Thursday. So, yeah, and I didn't have the time to make a continuing new talk in 15 minutes. So, yeah, so today I will talk about a project that was initiated, I think, something like 2005, or even earlier than this, with a discussion with Andrew Fletcher and Amba Shukurov in a taxi, I think. And in this taxi, I don't know where we were going to or from where we were coming from. Anyway, we discussed the role of thermal instability in the industrial medium. And the observational side of things was, from Andrew and Amba, that there is some mechanism in the ISM or in galaxies that seems to prevent the magnetic field always being frozen in, so that when you have a density enhancement, then you would naturally have a very strong magnetic field from the frozen-in approximation. So then we started elaborating this further, and as noted, several years have passed by, and we have managed to publish or send in one paper. So we are slow, but who cares? So first, some introduction to the business of thermal instability overall. So this is, of course, an old theory or model of the ISM proposed by Field, Golding and Harding in 1969. They realized the importance of thermal instability in regulating the warm and cold phases of the ISM. And this whole thing works. I mean, this is a sketch of how this thing is supposed to work, this FGH model. So this is the isobaric or condensation mode of thermal instability, and the whole business of thermal instability has been extensively studied by Field even earlier than this, 1965. But anyway, this is an application to the ISM. So thanks to thermal instability, which is described as the phase G here, this is the net heating and cooling function or balance, so that if L is positive, there is an excess of cooling, and if L is negative, there is excess of heating. And thanks to this thermally unstable branch in between the thermally stable phases F and H, then when a gas element or fluid element enters this phase, it's either overheated here or overcooled here, and it naturally moves either up here or down there. So here the density is low, and both temperature and density are low. This is the cold bumpy phase, and here with a temperature of 10 to the 4 kelvins and less density, this is the so-called intercloud warm medium. But this picture became quite soon, I mean in the beginning of 1970s, quite heavily altered by the observation showing that there is actually very hot gas everywhere in the ISM, everywhere in the galaxy. And somehow the hot gas had to be fitted into this picture, and that was done by McKee and Stryker in 1977, another seminal paper. And what is producing the hot gas is naturally the supernova explosions, which create these hot bubbles and expansion fronts. In these very early models, it was assumed that the supernovae were completely spherical, and they were actually not clumping in any way. They were more or less randomly distributed. So as can be seen from this picture, they seem to be everywhere. So the supernovae were thought to produce an ISM which is filled in by the hot gas, so that the hot gas filling factor is close to 60 or 70%. Nowadays we know that it's not so high, it's much less because of the clumping of the supernovae. They are not occurring randomly, but they are tightly correlated with the star formation sites. So in this sense, this picture is kind of outdated, and you could think of maybe one or two large bubbles like these ones, and the rest would be kind of free from the supernova activity, and then it makes some sense to still apply this FGH picture to the places where the supernova activity is not the dominating place. And then, of course, the ISM is high turbulence. So then what would happen for this, this FGH picture was completely static. It didn't take into account any sort of turbulence or turbulent pressure or turbulent motions. So it's clear that if there is a lot of turbulence that is pushing the gas elements around, many of them will be in the phase G, in the thermally unstable phase. And then it depends on the rate at which the thermal instability is capable of moving the gas to F and H from the G phase, and how much turbulence is pushing all the time to the unstable phase. So here we have done with Axel and Tony Mee, 2007, we made a paper about thermal instability without forcing. This is the case without forcing, and then with forcing, because we were set out to investigate whether turbulence, thermal instability can really drive self-sustained turbulence. So this is the case without any forcing, and this is now actually describing our cooling function. So wherever, so here is pressure and here is density and number density. So whenever there is an increasing slope, we have a thermally stable phase. And this is the thermally unstable branch, and this is actually marginally stable with a flat slope. So without any forcing, we have a pressure equilibrium between the two phases as predicted by FGH, and then two places where the gas wants to be. These are the phases F and H. When you put in some turbulence, I think here we already have a quite high forcing. So then you see that this complete pressure equilibrium, one pressure picture is destroyed, so that you have, if you would plot a PDF probability density function of the pressure, you would have wings, very large wings, wide wings in pressure distribution, and we observe gas also in the thermally unstable phase. But nevertheless, some of the signatures of the thermal instability persist in the highly forced case as well. And as I said, we were set out also to try to find out whether this turbulence generated by thermal instability could be sustained by itself, but it can't. So we observed the turbulence after the initial onset to decay. So we cannot expect thermal instability to be able to drive turbulence and sustain it. There are several other instabilities that can do it, like the magnetorotational instability, for instance. But thermal instability doesn't belong to this category. Then, this is the idea proposed by Andrew Fletcher and Anwar Shukurov way back in time. But the idea was, and this was based on observation of barred spiral galaxies, where especially in the regions of the bar, this is the publication written about this, especially in the region of the bar, when you apply the naive guess that the magnetic field is frozen into the gas and it should act as frozen in and be heavily increasing when there is either shear or compression. And it was realized that in these bars, this doesn't really happen very effectively. So then Anwar and Andrew were thinking of such a scenario, that there would be a mechanism that could condensation, drag in the field with itself to the cloudy component, and if the cloud or condensation would in addition be rotating, this would lead to rapid reconnection, and finally the large-scale magnetic field would be detached from the cloudy component. So one mechanism is naturally thermal instability and its condensation mode. And then we made some very simple simulations in pencil code trying to establish that this is really happening, and we used the same model as I showed already the results from. And in this, one thing to stress about this particular model, I mean, it is a finite difference code with a finite resolution. So how can we really resolve this condensation mode of the thermal instability, which is the thing? I mean, when the condensation starts, then you have to stop it. Either it is going to be a subgrid effect and it will crash your code. So the trick what we do, and what is now kind of a standard procedure, is to use the properties of the thermal instability itself. Because when, I mean here, chi is now standing for thermal conduction, gamma is the 5 Hz. This is number density, or I think this is now the how do you say that? It's from the thermal instability growth rate, or something like that. Beta, anyway, is the power law from the cooling function, what we were using. So betas less than 1 were producing the thermal instability condensation mode. So then you can write a criterion for the field wave number, that your grid, the largest permissible wave number in your simulation, which we denote with K1, must be larger than the field wave number. Then you will truncate the thermal instability at this wave number, so that it will stop condensing exactly there, so you can resolve it. So otherwise you cannot really even try to model the thermal instability with the finite difference code. Then there's nothing very special about these models. These are very simple ones. So first of all, we added a uniform magnetic field with this cooling function, thermally unstable cooling function, and added some vorticity initially to the system, which was kind of mimicking the cloud rotation. This was done at relatively small scales and with very small amplitudes. Then we, instead of plotting this sort of, going or trying to analyze things with the scatter plots of rho density and magnetic field and trying to correlate them somehow, we then further went on and defined a flux diagnostic, written down in here, where we calculate or divide the density field into bins of I. So there are n bins, and this I refers to each bin. Then we calculate the flux through each of these elements, gas elements with certain density. So we calculate the magnetic flux through them and scale it with the total flux plus the filling factor. Well, I will show you the plots of the how it looks like, how the density field looks like when there is thermal instability. And the fact is that the filling factor of the cloudy component is very small compared to the warm diffuse medium. So to be able to distinguish the cold component from the warm one, we need to scale with the filling factor as well. And this is how the flux diagnostic behaves with an artificially generated magnetic field. So if the magnetic field has, the magnetic field is proportional to the square root of density, the flux diagnostic defined as before looks like this. So it's monotonically increased. If there is an anti-correlation, so that it's the magnetic field is inversely proportional to the square root of density, then this happens. If there is absolutely no correlation at all, the flood diagnostic will be flat. So this is just to show you what to expect. So this is a typical run with the uniform magnetic field and just the thermal instability plot on. So you can see the segregation into this. This is all the warm diffuse phase, and these are the clouds generated by the condensation mode. And the arrows are showing the magnetic field. So the magnetic field is really dragged with the cloud contraction. This is with a Prandtl number of 100, so the magnetic diffusion here is quite weak compared to the kinematic viscosity. So the less the magnetic field will be able to diffuse, the tighter is the dragging effect. I mean, the more the clouds can drag the magnetic field. And then when you add this initial vorticity, this is what happens. So the more, then I of course should explain this rho omega. So rho omega was defined as the density at which the flood diagnostic abruptly changes from a positive monotonic correlation either to change the slope to a negative correlation or then do something abrupt change anyway. So this is what happens. So without any or very, very weak initial vorticity measured now with a kind of cloud rotation, nothing much happens. But when there is kind of a threshold in the cloud rotation, then you see that the flux is really detached from the cloudy component. And this critical velocity is somewhere around, I don't know, 0.2 or 3. And we made these experiments in 2D and 3D. And, this fits with Anvar's simple estimates of what should be happening. So I guess we can say that this scenario works in some extent. But of course, this was a very, very idealized setting. And it would be more interesting to know if the thermal instability, well, it can detach the large-scale field, maybe, but what will it do for the dynamo itself? Here is a galactic dynamo, what will happen? And instead of an imposed large-scale field, we then kind of put in a weak seed field and some forcing, because we knew that the thermal instability will not be able to keep up the turbulence, so we added some forcing. So the idea was to investigate both the effect on the small-scale dynamo and the large-scale dynamo. So with the helical forcing, we were planning to investigate the large-scale bit, and with non-helical forcing, the small-scale dynamo action. Well, even if the system is very simple, it brought some surprises to us. So nothing, something worked, but some other things didn't. And then we just have this cooling function with thermally unstable, and then for reference, thermally stable cooling function, which is scaled so that it produces equivalent net cooling integrated over all temperature ranges. So the thermally stable runs, first of all, they look like this. This is with weak forcing, and this is with high forcing. This is producing a Mach number of roughly 0.2 and this 0.7. This is the magnetic field. So there is really, with helical forcing, you get a large-scale magnetic field with a mode n equals 1. And the direction varies. So in this case, it's Vy in the direction of z, and here it swaps, and it's Bz as function of z. As function of x. I think both are as function of x. But anyway, different magnetic field component is growing. I think this was observed by Axel with a similar setting, except that it was isothermal and it didn't include any complicated heating or cooling. So then the flood flux diagnostic for such a system is almost completely flat. So the turbulent forcing is very ineffective, just a turbulence forced in the form of plane waves. So it's very ineffective of introducing any sort of correlation between the density and the magnetic field. So in principle, with all other experiments except the highest forcing, we get a flat diagnostic, so there is no correlation. And then what was the most surprising thing about these thermally stable rounds was that with the non-helical forcing we were not able to find any small-scale dynamo action up to the Reynolds number of roughly 100, which was completely different from a study from Axel and Tony Me and something else, I think, where they found dynamo action at the Reynolds number of 60. So we were also expecting to see it roughly there, but we didn't. And then we didn't have any time or resources for this particular paper to make any higher resolution runs, or then we didn't even want to use the artificial viscosities. So it was kind of out of the scope of the present study, and my student has extended this now to 130, and still we have no small-scale dynamo. So it's not a property of the thermally unstable runs, but it's a general property of interstellar cooling and heating functions. Thermally stable or unstable, no matter what. So the thermally unstable runs, they of course look very different, because now we have the condensation mode which is doing all the work by forming the clouds. So this is again with weak forcing, and this is with high forcing, and this is the magnetic field. So it's less obvious, or the large-scale magnetic field is not so nicely uniform anymore, but the large-scale field is there. The only difference now seems to be that the critical Reynolds number for the onset for large-scale dynamos is roughly doubled by the presence of thermal instability. So thermal instability is really bad news for the large-scale dynamo. And now these density contrasts are like 100 times larger here. So very quickly, the remaining slides. Thermal instability is much more effective in producing the correlation between the magnetic field and density. But even taken that it's really producing a lot of clumps with high density contrast, it's much, the density correlation agrees with the this scaling, not rho, square root of rho, but rho to the power of 0.2. So the correlation is much weaker. So thermal instability cannot really explain the tight correlations seen. And then, as you can see, with the highest forcings, actually, the flux diagnostic starts being or showing kind of a detachment at the highest densities. So this correlation is really breaking down with higher forcings. And again, no small-scale dynamo up to the Reynolds numbers we were able to go, but I think this has been observed before. There has been a study by Balsara et al. In 2004 who found out that the small-scale dynamo needs supernova rates of 8 times the solar neighborhood value to be onset. So the conclusions. So the very simple cases showed us that the scenario that thermal instability could provide a mechanism to detach the large-scale magnetic field from the dense structures may be working, and that the thermal instability is also affecting dynamo action, especially in the way that the large-scale dynamo becomes harder to excite. But then the thing what we don't really understand at all is that why the small-scale dynamo is so extremely difficult to decide with any wave function we have investigated so far. So thank you.
Interesting talk, Marit, and we have time for 2 quick questions.
In this study, you included compressibility.
Yes.
So the reason why small-scale dynamo is difficult to excite, but we have compressibility. We have shown 1997 that compressibility results in a strong increase of threshold generation of small scale diameter. So this is the main reason.
Still subsonic, right?
No, it's less.
Never mind.
Yeah.
Yeah,
It's
so
enough to
it's just, I
increase.
mean, with this, keeping just the ordinary viscosities, we are not able to even approach the supersonic regime. But you did, Axel.
Yeah.
I think in your study you had a...
Yeah, exactly. So
Yeah, it's enough
there's
to.
something else in the flow, which is different.
Yeah, because then the Reynolds number was, the critical one was roughly 60 in these units. We're using the same units, and it's
In
much
principle,
more
it's enough to
difficult to
increase degree of compressibility, which is the ratio mean square of divergence of velocity to mean square of curve of velocity square. And it's enough to increase in 30%, then you have increase of threshold generation in one order of magnitude, maybe larger.
She's just saying it has to do with the. She's explaining it has to do with the thermal instability, even if it's thermally stable.
yeah, well,
So there's a difference from exactly that fact. So I don't think that is explained by anything so far yet.
But it can be checked if compressibility decrease, and in that case it's easy to decide.
okay.
Okay, so if there are no more questions, let us thank the speaker. Let us welcome the last speaker of the session, Dr. Giuseppina Nigro from University of Calabria, who will talk on a shell model for turbulent magnetic dynamo.
Good morning, I'm Giuseppina Nigro, I'm a doctoral researcher at the University of Calabria. I'm going to present a model for a turbulent magnetic dynamo. You certainly know that the magnetic dynamo is the fundamental phenomenon to explain the generation of the magnetic field in many astrophysical systems. It's also possible to generate and study this phenomenon in the lab, as happened, for example, in the VKS experiment. The equation which describes the evolution and the generation of the magnetic field is the induction equation. So if you want to study theoretically this problem, we need to solve the induction equation. This is a nonlinear equation plus a momentum equation. This is a nonlinear equation as well. So when we deal with this problem using, for example, direct numerical simulation, the challenge is related to a very large Reynolds number if we want to reproduce the astrophysical natural system. So in order to overcome this difficulty, we built a new model which has the capability to describe a system with a very large Reynolds number. The starting point of the model is the scale separation. Essentially, we split the magnetic field and the velocity field in two contributions, an average part, V0 and V0, plus a floating part with variation at smaller scales. So the basic idea of this model is to solve the induction equation at large scales and in a consistent way solve the turbulent dynamics at smaller scales using a shell model. So we consider at large scale an axis symmetry situation in which we have a toroidal velocity and in which we can split, in which we can decompose the magnetic field in a toroidal and a colloidal component. Moreover, we consider a local analysis in which we can approximate the toroidal and the poloidal unit vector to a Cartesian unit vector, Ex and Ez. Essentially, we can write the large-scale velocity field and magnetic field in this form. The term which describes the effect of the smaller scales on the large scale is the turbulent EMF. Essentially, this is a correlation between the velocity field fluctuation and the magnetic field fluctuation. If we perform a Fourier transform of these fields in a k vector space, we can write the turbulent EMF in this form, and using in this k vector space this base, essentially we have chosen one unit vector along the k vector and the other two unit vector in the perpendicular plane. It's possible to finally write the turbulent EMF in this form. This is about the description of the system at large scales. For the dynamics at smaller scales, we want to use a shell model. Why the shell model? Because the shell models are able to describe the gross dynamical and statistical feature of a system with a very large Reynolds number. The main idea of this model is to divide the k vector space in which one considers the MHD equation in a concentric shell of exponentially increasing radius. In each shell, we consider two complex scalar variables, un and vn, for the velocity field fluctuation and for the magnetic field fluctuation. N is the number of the shell. We impose that in this k vector space the nonlinear interactions are local and they conserve quadratic invariant like total energy, cross helicity, and another quadratic invariant which corresponds, roughly speaking, to the magnetic helicity in a three-dimensional physical space description. So, using this model, we can write the evolution equation for the velocity field fluctuation and for the magnetic field fluctuation in each shell. The first, the second, and the third term on the right side are the nonlinear terms. This term and this one describe the effect of the large-scale magnetic field on the dynamics at smaller scales. Nu is the kinematic viscosity, is the magnetic diffusivity, Fn is the forcing that we have applied on velocity field fluctuation. So we can write the full set of the model equation in which we have written the turbulent EMF in a consistently form with the shell models. Moreover, the derivation at large scale is estimated dividing by the characteristic large scale, capital N. Fn is the forcing, is a correlated Gaussian noise, and so far we consider vanishing toroidal velocity. So far we described the alpha sway dynamo problem. So we need to solve numerically this equation. So we have used the Runge-Kutta-Numerica scheme, and in each simulation that I made, I just at the beginning let the system develop turbulence at smaller scales. After a while, when we are sure if the turbulence is fully developed at smaller scales, we just keep a magnetic field seed at large scales in order to check if the magnetic effects start to develop or not. The numerical results reveal a strong sensitivity of the system with respect to the magnetic Reynolds number and the dependence of the hydrodynamic Reynolds number. Depending on this parameter, the system can show different kind of behavior. In particular, if we have a low Reynolds number, for example, if we have a magnetic Reynolds number smaller than 60, no dynamo effect is developed inside of the system. Increasing the Reynolds number, we can see oscillatory dynamo states. Increasing more the Reynolds number, we can see magnetic reversals. And finally, increasing more and more, so for a very large values of the Reynolds number, we can see steady dynamo states. In order to better characterize these different dynamo regimes, we made the simulation in which we keep constant the kinematic viscosity. In this case, is equal 10⁻⁵, And starting from a large magnetic diffusivity, we decrease the magnetic diffusivity. And in this simulation, we check the behavior of this parameter, essentially the ratio between magnetic field fluctuation and the velocity field fluctuation. So decreasing the magnetic diffusivity is equivalent to increase the magnetic Reynolds number. So we have checked the behavior of this parameter for increasing values of a magnetic Reynolds number. Essentially, these parameters show a clear discontinuity corresponding to the magnetic dynamo transition. After that, these parameters show a power law behavior with a parameter alpha which change its values in a different dynamo regimes. So here is the diagram in which I have represented the hydrodynamic Reynolds number along X and the magnetic Reynolds number along Y. The different symbols represent the different kind of behavior of the system. In particular, the red stars indicates the states in which the system, in which no dynamo effect is developed inside of the system. The green circles define a numerical Reynolds number domain in which the system is an oscillatory dynamo state, while the blue squares define a Reynolds number domain in which the system is in a magnetic reversal state. And finally, the azure rhombus define a domain in which the system is in a steady dynamo state. So essentially, these results show the critical role that the magnetic Reynolds number play in this process for a different kind of dynamo regimes, and also the dependence of hydrodynamic Reynolds number. The model gives us also the possibility to study the dynamo transition in a very wide range of values for the critical parameter. So we have studied the dynamo threshold for a very wide range of values for the Prandtl number, and we have obtained the stability curve. Essentially, these results show a very weak increasing in values of the critical magnetic Reynolds number for increasing values of this parameter. This is the inverse of a magnetic Prandtl number, in a range in which this parameter is larger than 1, while for decreasing values of this parameter, we can see a strong monotonic increase in values of a critical magnetic Reynolds number. This increase could be related to the need to have very small and smaller diffusivity in the case in which we have large kinematic viscosity, to have field fluctuation at smaller scales large enough to consistently trigger the turbulent EMF for the dynamo on site. We have also found an hysteretic behavior across the boundary transition, revealing the subcritical nature of the dynamo transition as described in this model. So, the model gives us also the possibility to reproduce a very long time series of reversal, which can be statistically analyzed, making a comparison with the paleomagnetic data analysis. Essentially, in the case in which the system displays magnetic reversals, we have calculated the probability distribution function of the persistence time. This function shows a power law behavior in an appropriate range, and this power law behavior is in agreement with the paleomagnetic data analysis made in 2007 by Sorriso Baldo. This behavior shows the presence of a long-time hidden correlation in a chaotic dynamo process, revealing some degree of memory. Moreover, the numerical results show the tendency of the system to develop longer persistence time for increasing values of the large-scale magnetic field. This is clear if you look at these two different probability distribution functions obtained for two different cases. The red one is the probability distribution function obtained in a case in which we have not a very large magnetic field, And the green one is the probability distribution function of the persistent time obtaining in a case in which we have larger magnetic field strength. It's clear that longer persistence time have higher probability of occurrence for larger values of the large magnetic field. This result is an agreement with the results obtained in other model made on 2005 by Stefani and Gerber, and also this is an agreement with data analysis made by Terbuno on a geomagnetic intensity reference. So, here is my conclusion. Essentially, I present a model in which we solve in a simple way the induction equation, and in a consistently way we solve the turbulence dynamics at smaller scales using a shell model. Here are some numerical results, and probably I think that the most important results is related to the capability of the model to describe a system with a very large Reynolds number, and also is related to the capability of the model to describe very long-time series of magnetic reversals. That's all.
Thank you, Giuseppina, for a good talk. And yeah, questions?
Could you please demonstrate again dependence of critical magnetic Reynolds number for inverse Prandtl number? Yes, please. And what's the result? So, for large Prandtl number, critical magnetic Reynolds number increase. Is it true? For large Prandtl number, critical magnetic Reynolds number increase. And as I know, this is what in direct numerical simulation and in Kazantsov equation, results just opposite. It's a little bit strange.
This is for the large scale dynamo, not for...
For large
I have
scale. No, how you can, if you've got shell dynamo, how you can distinguish between
Well,
large
just couple it for me. I know, it's the other way, the small scale dynamo.
I don't know, I have checked with another work made by Ponti, and using different kind of numerical code, find the results very close to this, in a range covered by this work.
And how you obtain this result? This is a result of this shell model, or?
Not just the shell model. It's the results of the full model.
Because it's an agreement also with numerical simulations by Axel, by... So this result also in disagreement with numerical simulations. When you decrease magnetic Prandtl number, the critical magnetic Reynolds number should be increased.
It does.
And here,
It's here minus 1 plotted.
Right
It's the inverse of the magnetic.
Sorry, yeah. Okay, but you do have large scale dynamo action, you said. You do have large scale dynamo action.
Yes.
Okay. And then of course it should be independent. That it can increase with simulations. Think. But what I don't understand is why it's oscillatory. Didn't you not say it was oscillatory?
Oscillatory dynamo, you mean?
Yeah.
Yeah, I mean, this is the first regime that you found.
Yeah, and that is maybe new, right? And we don't see that in simulations. That is oscillatory.
I have one question. You showed the PDF and compared it with the results of Luca Soleso-Balbo. Did you also check the clustering properties of reversals, which was shown?
In some cases, yes, but not for the full set of simulation that they made.
And have you seen some similar result
Yeah.
as Luca? Okay.
Yeah.
So you have a clustering property.
Yeah.
Right? Okay.
Does your full system, the large scale and small scale, follows all conservation laws?
Pardon me?
The full system, so you have the equation for large scales and for
Yes.
small scales.
Yeah.
Does it follows the conservation laws? the magnetic helicity conservation?
I mean, in a shell model, you don't have a real magnetic
I
helicity.
understand. The who model, the question is.
Yeah.
Have you checked that the who model
Yeah.
conserves?
Yeah, but it's not the real magnetic helicity. It's something equivalent.
Yeah, but
You have a proxy of magnetic helicity. And is that
Yeah.
conserved for large scale and small scale fields?
together.
Together, yeah?
Yeah.
So then,
So you have controlled the exchange of helicity and energy of the large and small.
Yeah.
Just a comment on this magnetic Prandtl number confusion. As the magnetic Prandtl number goes up, you expect the dynamo to go to smaller and smaller scales, right, to the resistive scale. So it's not surprising that as she puts up the magnetic Prandtl number, she finds it harder and harder to get a large-scale dynamo, because it's all going, like the Kazantsev model says, it's all going to the resistive scale. So it's kind of consistent, it's just...
But it should be, doesn't depend, I think, for large scale dynamo. 5 dynamo means that it doesn't depend from this parameter at all.
No, because you're sending everything to the resistive scale. As you go to higher and higher magnetic Prandtl number.
It is large, if it is large scale dynamo, it's known that any information about molecular, how to say, scale, values, it disappears from zero.
But not the way she's doing it, no.
Strange.
Concerning this issue, your model, your shell model is local?
Local in a K vector space.
Yes. And so, at large magnetic Prandtl number, we expect some non-local, highly non-local energy transfers. So, I think...
It's not local, the energy transfer between small scales and the large scale.
Yes, but we would expect some energy transfer to smaller scales in a non-local way, which cannot be reproduced by such local model.
I mean, this model in a range of smaller scales assume local interaction. So you have an energy flux from the larger scales in a small scale range to the smaller scale, to the dissipative range.
Yes, but what I mean is that the dissipative scale for the magnetic field stays very close to the viscous scale, even if yes, but
it's yeah. I mean, you have a Kolmogorov power law
but even for the small scale field,
at smaller scale,
and this. Because there is the possibility to use non-local shell models, and in this case you would probably have different results.
Probably,
In 2006 we have introduced a very similar model, alpha squared dynamo model with the additional shell model, in order to simulate small-scale dynamo, and we find out that there is a very important parameter of the model which is controls the scale separation between large scale and turbulent scale, where you inject the energy, and this reversal you find out it seems to be very sensitive to this scale separation.
yes, in fact, I make different simulation changing this parameter. Right now is equal to 10. This is described the scale separation because the K0 is the typical small scales and capital L is the typical large scale.
And how
And there
this...
is some difference between the simulation, but I didn't have time to show.
And did you find the difference between in this statistics for reversal? Does it depend on this parameter or not?
I mean, I didn't check. I just checked that the different kind of dynamo regimes changing for a different Reynolds number, changing also this parameter.
But it would be nice to see the
Yeah,
difference.
I will do that.
Yeah, so we have the last question from you.
Just a comment on the critical Reynolds number and Prandtl number. In shell models, if you don't have such shell models which couples with large scale velocity but just small scale shell models, then the plot for high Prandtl number is roughly the same. which basically roughly agrees with what she is saying. If you have just simple shell model, not something coupled to large scale.
Why?
Why? What do you mean why?
Why is it?
If that's true, then that is at odds with everything else.
Sorry?
If that is true, then that is a serious deficiency in shell model, because that's at odds with everything
I mean,
that's known about.
do you have any other evidence of how this should behave for high?
IPM? Yeah, lots of evidence. Fast
From
dynamo.
where?
The whole of fast dynamo theory is based on what happens at high PM. Everything is smaller and smaller scale.
Sorry, which theory?
Fast dynamo.
The whole fast dynamo theory is exactly that problem. You fix the velocity field and you take Rm going to infinity. Well, that's the question, yeah.
But then to fix that problem, you may use non-local shell models,
I mean,
which also exist.
yes, but the shell models generally capture the exponents pretty well. You don't need something more complicated than a local shell model
I mean,
to get the, even the intermediate exponents pretty well.
Yes, but the problem with shell models, it is that the energy transfer goes from one scale to the next ones, or the two next
yeah,
ones.
but I mean, I have used the shell model with a local interaction just to describe the turbulence. And the dynamo effect is described by the scale separation and stuff. So I don't need to use a non-local shell model at this point.
So this talk has generated a lot of questions, and if you are not interested in coffee, we can have 15 more questions. But so if that's not the case, then let us thank all the speakers for this.